Okay, so here is the walkthrough for the uncertainties multiple choice level 6. So we're now looking at various ways of combining uncertainties, dealing with all the different things we've looked at in terms of absolute, percentages, and combining them for different quantities. Here is question 1. So this time you are looking for a value for upthrust. So the value for upthrust is going to be the difference in value of the reading for the weight of the block out of the water and the weight of the block once it is fully submerged. The difference between these two values for force will give us our upthrust. So we start by saying, well, okay, the value for actual upthrust in this case is going to be our block out of the water, which is 1.2, minus our block fully submerged, which is 0.8, giving us a value of 0.4 newtons. Okay, now we know that's probably right because if we look at the options that we've got, we can see that they're all 0.4 newtons. Okay, so what we now say is, well, all right, what is the uncertainty in each of these readings? And remember, the uncertainty is plus or minus the smallest scale division. So if we look at this scale here, for example, we can see that the uncertainty here is going to be plus or minus 0.05 newtons. And equally, when we look at the scale on this one, we've got exactly the same precision. So we've got an uncertainty of plus or minus 0.5 newtons again. So therefore, the total absolute uncertainty in our reading here is going to be plus or minus 0.1 newtons, okay? Because the value for upthrust is given by taking one value for force from another. They're measured in the same unit, and therefore we can simply sum their uncertainties. Okay, so what we know then is that our answer must be 0.4 newtons plus or minus 0.1, and we know that the answer is going to be answer D, because when we have these absolute uncertainties, it's only reasonable to estimate to one significant figures. So that is why our answer will be D rather than C. Okay, so now we're looking at having repeat readings and using those to find our uncertainties. Okay, so remember when we look at this, the absolute uncertainty from a range of readings is plus or minus half the range. Okay, so that's how you determine the uncertainty when you have got a set of repeat readings. Okay, so first thing to do is to work out the absolute uncertainty in our value for V. All right, so in that case, we know that the absolute uncertainty is our maximum value of 3.4 minus our minimum value of 3.34, and divide that range by 2, giving us an absolute uncertainty of 0.03, or rather plus or minus 0.03 volts. If we then turn that into a percentage, so the percentage uncertainty in V will be that value of 0.03, divide it by the average of 3.37 and times it by 100, and we have a percentage uncertainty of 0.89% in our value of V. We now go through exactly the same process with our I. So we start with the absolute uncertainty in our value for I. So again, we look at the range. So 4.05 minus 4.03. I know this is in milliamps, but again, because they're both in milliamps, we don't have to include the times 10 to the minus 3 here. We divide that range by 2, and that gives us a value of plus or minus 0.01 amps for our absolute uncertainty. Our percentage uncertainty in I is then this absolute, 0.01, divided by our 4.04, and again, we can omit the times 10 to the minus 3 because they're both in milliamps. We multiply that by 100, and that gives us a percentage uncertainty of 0.248%. Okay, so now we've got a percentage uncertainty for V, a percentage uncertainty for I, therefore the total percentage uncertainty is going to be the sum of those two. So we add the 0.89 to the 0.248, and that gives us a value of 1.14%. If we now actually calculate our value for R using our average value for V of 3.37 and dividing that by our average value for I of 4.04 times 10 to the minus 3, because this is measured in milliamps, then we get a value for R of 834.15 ohms. So we can see that that's probably right because all four options are 834. The last step then is to work out the absolute uncertainty in that value of r. So to do that, we take our 834.15 and we multiply it by 0.0114%, and that gives us 9.5. So that means that our best value from best option from the choices that we've been given is 834 plus or minus 9 ohms for our value for resistance, and that is C. Here we're now using the reading from a micrometer to determine the area of a wire. Okay, now remember the thing with a micrometer is that they will measure to plus or minus 0.01 millimeters. So there is our absolute uncertainty. In this case, that is the absolute uncertainty in diameter. Okay, so it's our absolute uncertainty in diameter. So if we start by working out the percentage uncertainty in our diameter, so we take our absolute, which is our 0.01 millimeters, and we divide it by our actual. So if you look at our micrometer here, we can see that there is a reading here of 0.27 millimeters. So our percentage uncertainty is 0.01 divided by 0.27 multiplied by 100, and that gives us a percentage uncertainty of 3.7% in diameter. So if the percentage uncertainty in D is 3.7%, we know that the percentage uncertainty in R will also be 3.7%. Because in finding our value for R, we are dividing D by 2, and therefore that doesn't carry with it any additional or lack of uncertainty. So the percentage uncertainty in R is also 3.7%. But we have been asked to look at the area, and we know that area is pi r squared. So whilst the percentage uncertainty in R is 3.7%, the total percentage uncertainty in our value for A is going to be 2 times that. So that's going to be 7.4% because we have squared the R. So we've got the 3.7% R uncertainty plus an additional 3.7% uncertainty in R. So our total percentage uncertainty in A will be 7.4. So our last step then is to actually calculate a value for A, okay, so using pi r squared. We therefore divide our value for D by 2, which gives us 0.135 times 10 to the minus 3, because remember we're working in millimeters. We square that, and that gives us a value of 5.7 times 10 to the minus 8 meters squared, which again, if we look at two of our values, C and D, we know we're probably on the right track. So the last thing then to do is to work out 7.4% of that 5.7 times 10 to the minus 8. So 5.7 times 10 to the minus 8 multiplied by 0.074 gives us a value of 4.218 times 10 to the minus 9, or that's 0.4 times 10 to the minus 8. So we can see therefore that our answer for the area is 5.7 plus or minus 0.4 times 10 to the minus 8 meters squared, which is D. Okay, so here we've been given a value for current, or rather a range of values for current, repeated readings, and a value for resistance, and we're being asked to record the power of our resistor. So given that we've got current and we've got resistance, we know that we're going to be using P equals I squared R to calculate this. So let's begin with looking at the uncertainty in I. Here again we've got repeat readings, so in order to find our absolute uncertainty in I, we firstly need to do plus or minus half of the range. Okay, so our range in this instance is that 1.73 maximum less the 1.56 minimum divided by 2, giving us an absolute uncertainty of plus or minus 0.085 milliamps. Okay. If we then convert that into a percentage, we can say, well, therefore the percentage uncertainty in I will be our absolute, 0.085. We divide that by our average value, okay, and when you actually calculate the average value, the average value for I comes out at 1.65, okay? So we divide that by 1.65. Remembering again, we can omit the times 10 to the minus 3 because they're both measured in milliamps. Times it by 100 gives us a percentage uncertainty in I of 5%. If we then look at the uncertainty in our value for R, well, we are told that the tolerance for R is plus or minus 1%. So we've got a percentage uncertainty in R of 1%. And therefore our total uncertainty, or rather total percentage uncertainty in power, is going to be the percentage uncertainties combined. But once again, we've got I squared. So actually we've got 5% uncertainty from the first value of I, we've got a second 5% uncertainty from the second value of I, and then we've got the 1% from the value for R, giving us a total percentage uncertainty of 11%. When we now actually work out that value for power, we take our average current, so 1.65 times 10 to the minus 3, and then we square it. We multiply it by our value for resistance, which is 4.7 times 10 to the 3. And when we do that, we end up with a value of 0.0127 watts, which is approximately 13 milliwatts. Okay, so we look there on, we've got one of our answers there as 13 milliwatts. Okay, we then work out our percentage uncertainty, so 11% of 13. We're working out our absolute uncertainty. So we take our 13, or if we take our actual value of 0.0127, or rather, let's work in milliwatts from here on out, 12.7 multiplied by 0.11 gives us an absolute uncertainty of 1.4, or rather plus or minus 1.4 milliwatts. And therefore, when we look at our answers, the value that we've got that is closest to our options is answer C, which is 13 plus or minus 1 milliwatt. And the last question here looks at comparing which ammeter we should use when we're faced with digital or analog. Okay, so a couple of things to draw your attention to here, making sure you are familiar with the term accuracy. Okay, what accuracy actually means. Remember, accuracy is the closeness of a reading to its true value. Okay, we've also got options discussing the uncertainties in the measurements. So if we take, let's start with the uncertainties because we can actually work those out and deal with them. Option B suggests that the analog ammeter is better because the uncertainty of the measurement will be lower. So if we look at our uncertainty here, in our analog meter, we can see that each division here is 1 microamp. So we've got 1 microamp and absolute uncertainty. If we divide that by our actual value, which is about 34, okay, 34 microamps, and then we times that by 100, then what we find is we end up with a value of 2.9%. So the percentage uncertainty from the measurement on the the analog meter will be 2.9%. When we compare that to the 5% from our digital, we can already see that the uncertainty in this one is going to be lower. So we can therefore disregard that bottom statement because we know the uncertainty of the measurements will not be the same. And we can categorically say that actually the uncertainty of the analog ammeter is lower, and therefore that is our option B. So the reason that we can discount option D here is because we know that option C is because we know that the accuracy of the two measurements can't possibly be the same. Remember, accuracy is about how close it is to the true value. The question tells us that it's about 30 microamps. The reading on the digital ammeter is closer to 30 than the reading on the analog multimeter, and therefore we can discount option C. However, we don't know for certain that the digital ammeter is always going to be higher, but we can definitely say that the uncertainty will be lower. So that is why in this option, option B is the best one to choose.